Okay, so the next question that we have here is that show that the Signum function, which is given by, you want to show that basically question number 5 is you want to show that the Signum function given by f of x is equal to basically 0 if x is equal to 0, it's equal to 1 if x is greater than 0, and it's equal to -1 if x is less than 0, which is actually a very useful function. It can be a very useful function in many sorts of applications. For example, in electronics, you could do all kinds of things with this function. For example, in digital electronics or wherever you go, you can find some application for this function. We want to show that this function is neither 1, 1 nor onto. Is neither 1, 1 nor onto. Right? Now, first of all, the Signum function is basically a function like this. Although basically the definition is clear, but basically the name is the Signum function. The name is the Signum function. It's a function from f from R to R, and it's defined by, f of x is equal to basically 1 if x is greater than 0, 0 if x is equal to 0, and -1 if x is less than 0. And so based on that, and so you know that the domain of the Signum function is R, and the range is, so you can see that over here this is the domain of the function. This over here is the range, is not the range of the function, but it is the codomain of the function, which is, of course, in many cases it can be different from the range of the function. And as you can see, the range of the function can be either 1, 0 or -1, which means that the range of the function is basically the set -1, 0 and +1, right? And so based on that, so you can see that the codomain is the set of all real numbers. The range is only these 3 numbers, which means that all the other numbers in the set of real numbers, which are not any of these 3 numbers, is basically a member of the codomain, which is not the image of any of the elements in the domain of the function. I need to close my window. And so based on the fact that there are all of these elements in R that are, for example, you can say, I don't know, -2, for example. -2 does belong to R, but it's simply not an element of the codomain that is basically the image of any element in the domain of the function. So you can say, but that there does not exist an element basically x belonging to R, such that f of x is equal to, well, the notation here is I don't really know the notation. The notation has not been given here. Let me see if I can find the notation for the signum function. It seems that it is represented as SGN. It seems that it is represented as SGN or SGN or sign of X basically. So signum, so basically the word signum is actually, you have the word sign in it, right? And the function is actually doing the same thing. Based on the sign of X, it's deciding whether your output is going to be 1, or based on the sign of X is deciding whether your output is going to be -1, meaning that if the sign of X is any number which is a positive number, then your output becomes 1. If X is any negative number, then your output becomes -1. If X is 0, having no sign, then what that means is that then your output becomes 0. And so I suppose for the same reason it's been called the signum function. And so you have the word sign in there. And so the notation of the function has simply been selected as SGN of X. So we can say that then but there does not exist an element X belonging to R such that f of X is equal to SGN of X, which is equal to, for example, -2, and therefore basically f is not surjective. F is not surjective or basically onto, right? Now there is, and the signum function basically, as long as we are talking about the signum function itself, so you can imagine that the graph of the function is basically something like this, meaning that suppose that you have, this is 1 and this is -1, and the graph of the function becomes, for 0 you have the output that is at 0, and then you have basically, this is your output for all the positive X's, and this is your output for all the negative X's. So this is y is equal to 1, and this is y is equal to -1, and so this is the graph of the signum function. The graph of the signum function, and f of X is equal to, you can say that f of X, it seems that you can define the function in terms of the absolute value function, meaning that you can say that f of X is equal to the absolute value of X divided by X, and basically it's also f of X is equal to 0 for X is equal to 0, and this is for negative and positive X's, right? So which means that basically if you have, for example, suppose that X is equal to -2, then f of X becomes, f of -2 becomes, based on this definition, the absolute value of -2 divided by -2, that gives me 2 divided by -2, which is equal to -1, right? So that is, you can simplify this becomes a -1, and 1 divided by -1 is equal to -1. and it applies to any negative number. Any negative number you input here, you will get a negative 1. Any negative number you input here, you will get a negative 1 output. Suppose that x is a positive number, for example 5, then f of 5 becomes the absolute value of 5 over 5, which is equal to 5 over 5, which is equal to 1. Meaning that for any positive number input, your output is going to be 1. That is the Signum function. Now the problem here is that in order for the function to be 1, 1 or injective, basically what needs to happen is that for every x and x1, let's say, and x2 belonging to the set of belonging to the domain of x, to the domain of f, then if f of x1 is equal to f of x2, that should imply that x1 is equal to x2, but that's not the case, because for example you can see that f of negative 1 is equal to negative 1, and also f of negative 2 is equal to negative 1, and also f of negative 3 is equal to negative 1, and so on and so forth. That means that the distinct members of the domain of the function do not have distinct do not have distinct images in the codomain of the function. So which is not the case, and therefore you can say that f is not basically injective. F is not injective. So that is this that is the Signum function. Now the next question that we have here is a couple of other questions that are not related to these very popular functions like the Signum function or the modulus function and so on and so forth. We have, for example, let a be equal to basically 1, 2, 3, and let b be equal to this is another set 4, 5, 6, and 7, and let f be equal to, let f as a function be equal to 1, 4 and 2, 5 and 3, 6 be a function from a to b. So let these two be the case, and let this function be a function from a to b. Show that f is 1, 1. Okay, so now this problem is, well, not that complicated at all, because basically you have the set A is 1, 2, 3 and B is 4, 5, 6, 7, and you see that f is a relation or a specific type of relation that you can call a function from A to B. That is basically the set 1, 4, 2, 5, 3, 6, and you can see that the distinct elements of the domain have distinct images in the codomain of the function, which is 1 is mapped to 4, 2 is mapped to 5, and 3 is mapped to 6. So meaning that there is no two ordered pairs in F that have the same first element, meaning that, for example, or basically meaning that you could actually have some f, for example, here that would still be a function. You could write, for example, 1, 4 and, for example, 2, 4. And what this means is that and so on and so forth, and some other elements. And in this case, then you could say that f of 1 is equal to 4, and f of 2 is also equal to 4, which means that the distinct elements in the domain of the function do not have distinct images in the codomain of the function. But and basically let me take a look at the solution here as well to see how they have solved this problem. This is question number 6. So the answer here is given that A is equal to this set and B is equal to this set, and f is defined as this function. So f of 1 is equal to 4. So let me erase all of these. So you can say that basically f of 1 here is equal to 4, and f of 2 is equal to 5, and f of 3 is equal to 6, right? So it is seen that the images of distinct elements of A under F are distinct. It is seen that the images of distinct elements of A under F are distinct. Hence the function is 1, 1, or f is basically 1, 1 or injective. So this was simple. Now the next question here is question number 7. You want to show that in each of the following cases, state whether the function is 1, 1 onto or bijective. So for example, let's say that you have a function, part 1 of number 7 is basically f is a function from R to R, defined by f of x is equal to 3 minus 4x. 3 minus 4x, right? Now first you need to show whether this function is injective. Now to show whether this function is injective or not, you do need to show that for every x1, x2 belonging to the domain of the function, if f of x1 is equal to f of x2, that implies that x1 is equal to x2, right? Now if I assume that f of x1 is equal to f of x2, then that means that basically based on the rule of the function, I have 3 minus 4x1 is equal to 3 minus 4x2. So then you can simply simplify these from the two sides of the equation, divide both sides by -4, gives me x1 is equal to x2, and therefore f is injective. Now if you want to show whether f is surjective, now you can see that the codomain of the function is the set of real numbers. You need to show that every member of the real numbers you need to show that there is no member of the set of real numbers that has not been mapped, that is not basically an image of some element in the domain of the function, meaning that every member of the set R has been mapped to some R in the codomain of the function. Or you need to show that basically every member of the real number in the codomain of the function is the image of some element in the domain of the function. Now, for such cases, you need to find a counterexample, and you need to find a counterexample and show that that's not the case, or you need to show that for every 3 minus 4x, which is basically your output, there is some x that is mapped to that, right? So now, in order to do exactly that, what you need to do is you need to find the inverse of your function. If you find the inverse of the function, then you can easily show that basically every output is mapped from some input from the domain of the function. So how do we do that? We said that f of x is equal to 3 minus 4x. We said that f of x is equal to 3 minus 4x. So f of x is your output and x is your input, right? Now, if I call f of x the output of the function, let's call it y, for example, for the time being. Let's say that f of x is equal to y. That means that basically 3 minus 4x is equal to y. And now, how can I find x in terms of y? Meaning that I can write negative 4x is equal to y minus 3, and then divide by negative 4. Then that will give me x is equal to y minus 3 divided by negative 4. Or I can write x as basically 3 minus y divided by 4. So that means that x is equal to negative minus y divided by 4. So what that means is that basically every value that what that means is that every y, now this x is basically the input of the function, right? So we took y as the output of the function. So that means that you can say that for every real number, for any real number y, you can say that for every real number y in R, there exists basically 3 minus y divided by 4, 3 minus y divided by 4, which is of course a very good way of saying what I wanted to say, but I actually didn't have a good way of saying that. There exists 3 minus y divided by 4 such that f of basically 3 minus y divided by 4 is equal to y, right? So what that means is that now what I have done is that I have I have actually found the inverse of this function, meaning that I have written f of x is equal to 3 minus 4x, which is basically the rule that was given to me by the question itself. Now, if I assume that f of x is equal to y, or the output of the function is equal to y, this is the value that you will get as a result of any input that you give to this function. So you know that basically, based on the question, you know that you can input any x into this function, any input of the real numbers, which means that basically the input of the function is the set of real numbers, and the output, you don't really know if that's the whole set of real numbers, and that's what we want to find out here, this part. We know that basically x can be any real number, and you can input that, and it will give you some output which is called f of x. Now, in order to make sure that every member of the set of real numbers, which is the codomain, is going to be mapped to from some element in the domain of the function, I have to go the other way around. I can't go from this side to this side. I have to get back from this side to this side. That's what I need to do. So to get back from this side to this side, I have to find the inverse of the function. The inverse of the function gives me tells me basically what y I have to choose here in order to get what x over here. The function itself tells me what x I have to choose here in order to get what y over here, right? So now going with the inverse of the function, which is well, the inverse of the process of the function, I write 3 minus 4x is equal to y, and then I can use some algebra and write over here negative 4x, for example, is equal to y minus 3, or x is equal to y minus 3 divided by negative 4, or x is equal to y, or 3 minus y divided by 4. That gives me basically that gives me some relationship between that gives me x in terms of y, but this relationship over here gives me, as you can see over here, if I take f of x as y, this gives me y in terms of x, 3 minus 4x, right? So these are inverse processes. These two are actually inverse processes, meaning that this relationship gives me y in terms of x. This relationship gives me x in terms of y. So now I have a way to get back from here to here, meaning that if I know that my x is equal to, for example, 3, I know what y, I can calculate what y I have to use in order to get that x, right? And of course, you know that basically if I say that, for example, if I say that f of x is equal to x minus 2, what this function does is that this function, whatever input I give it, it subtracts a 2 from that input and gives me an output accordingly. Meaning that if I give it a 2, it gives me a 4. I'm sorry, if I give it a 2, it gives me a 0. If I give it a 2, it subtracts a 2 from this 2, it gives me a 0. If I give it a 4, it subtracts a 2, it gives me a 2. If I give it for example, a negative 2, it subtracts a 0, it gives me a negative 4, and so on and so forth. So now using this relationship, I know that for 2, what output I can get from this function. I know for 4, what output I can get from this function. I know that for negative 2, what output I can get from this function. But there is no way for me, based on this relationship, there is no way for me to know what input I can get for 2, right? I do not know what input I can get for 2. For y is equal to 2, what input I can get, I cannot calculate from here. So in order to know that, I simply go and calculate the inverse of this function. I simply write y is equal to x minus 2, and then calculate x in terms of y, meaning that I write x is equal to y plus 2. Now I know that any x that I'm looking for, or basically any y, any x that I'm looking for, I have to take my y and add a 2 to it. So now I know that, for example, my y is 2 over here. And I didn't know basically what x I have to supply to get to a 2, right? So now I can do the same thing over here. Now my y is equal to 2. I add 2 to my y and I get a 4. That means that I know that I have to supply the x is equal to 4 over here to get basically the y is equal to 2 in the same function, right? So that is the process of the inverse. And moreover, you can see that over here, since we are saying that f of x is equal to x minus 2, if I calculate, since I'm saying here that y is equal to x minus 2, so then I can say that, then over here I can say that x is equal to y plus 2, as we saw over here. Now if I can write the same function in terms of its inverse, meaning that I can, instead of x, I can put a y plus 2 over here. F of y plus 2 is equal to x, which is equal to y plus 2, and I have a negative 2 over here, and you can see that f of y plus 2 gives me a y, right? So what that means is that when you rewrite your function in terms of the description of the inverse of the function, then you will always get your output. You will always get your y, because over here you are giving it whatever it is that you have to give to the function to give you that output. And what that means is that, and what that means here is we are saying that for every real number y in R, there exists 3 minus y divided by 4, such that f of 3 minus y divided by 4 is equal to y. That means that every y over here is practically covered, meaning that there is no y that is left out in this function, which means that every y that you can find in this set, in the codomain of the function, is going to be the image of some element in the domain of the function, which means that there will be no elements in this set which is left alone, which is not an image of some element in the domain of the function. And that means that basically the function is surjective or onto. So that tells you that basically f is onto or basically surjective. Now because the function was injective, and also surjective, you can say that f is bijective. You can say that f is bijective. So that is part 1 of this question. Now part 2 of this question. Part 2 of this question is basically we have another function here, which is f, a function from R to R, defined by basically f of x is equal to 1 plus x squared. Now this is a little bit different, because in order to get back to the function, in order to write the inverse of the function, you have to use the square root function. And then in using the square root function, you might get into a little bit of trouble, meaning that you might actually not be able to get back exactly the way that you got there. So the function is, what this function is helping you with is that you have some domain here and you have some codomain here. And based on this rule, you also have some range here. Sometimes this range and this codomain become the same thing, sometimes not. Now what this function is doing for you is that it gives you a way. So for example, here the domain is the set of real numbers. The codomain is the set of real numbers. What this function is doing for you, based on some rule, it helps you to get from here, which is the domain, it helps you to get from here all the way up to here, from some element to some other element. This element is called the image, the pre-image. This element is called the image. The pre-image under f, for example, this is the pre-image under f, this is the image under f. So this function does this for you, meaning that it allows you to get from here all the way up to here. Sometimes, and in the previous example, you saw that the function allows you to get from there, from the domain to the codomain, and also back to the domain without any trouble. And also the function was such that basically every element in the codomain was actually an image of some element in the domain of the function. Now let's see if this function actually does the same thing for us, right? So now in order to solve this problem, there are two things that you need to check. If your function, you need to check whether your function is 1-1 or injective. You need to know whether your function is onto or subject or surjective. And you also, if these two are the case, then you can say that your function is bijective. You can say that your function is bijective. If both of these are the case, then you can say that your function is bijective. Okay, so now in order to decide whether f is basically injective, what you need to do is that basically the condition is for every x1, x2 belonging to x, if f of x1 is equal to f of x2, then that implies that basically x1 is equal to x2, right? Which means that let's suppose that basically f of x1 is equal to f of x2. I want to know if that is true. So I assume that this is true, and then if I can prove that the second part is true, then that means that basically the whole statement is true. So if f of x1 is equal to f of x2, okay, so now let's suppose that f of x1 is equal to f of x2, which means that basically 1 plus x1 squared is equal to 1 plus x2 squared. And you can simplify this, write it as x1 squared is equal to x2 squared. And since basically x belongs to the set of real numbers, x could be a negative number, it could be a positive number, and therefore x1 is equal to plus or minus x2, meaning that let me write another step here, meaning that we can take the square root of x1 squared and take the square root of x2 squared, and the square root of x1 squared is equal to plus or minus x1. The square root of x2 squared is plus or minus x2, which means that x1 is equal to plus or minus x2. Now this means that x1 could be equal to x2, or x1 could be equal to negative x2. And if that is the case, then basically then that proves that basically this statement is not true. And if this statement is not true, then you can say that f is not 1 1 or basically injective or injective. Now, in order to check whether f is surjective, you need to show that every element in the codomain of the function, which is this set over here, is an image of some element in the domain of the function. And we argued before that for this purpose you can always find that the inverse of the function. So the function is f of x is equal to 1 plus x squared. F of x is equal to 1 plus x squared, right? Okay, so in order to see if basically if f of x is equal to 1 plus x squared is surjective or not, so using algebra you could get into trouble, as I did. So you need to use some other method. So basically sometimes the graph of the function is much more helpful in basically recognizing all of these things. Meaning that, for example, if you want to know if a function is surjective, you can easily see it on the graph of the function. Meaning that, for example, f of x is equal to 1 plus x squared is going to be some function like this. Right? So some function like this is going to be f of x is equal to 1 plus x squared. And what that means is that basically what we are saying here is that basically f goes from R to R, meaning that your domain is the set of real numbers, your codomain is also the set of real numbers. And you can see that the output of the function is all in this area of positive numbers greater than or equal to 1. So the range of this function is actually, the range is actually 1 all the way up to positive infinity, right? The range is actually this set. It goes from 1 all the way up to positive infinity. That means that all of these values in the less than, basically, which are less than 1, are simply not a part of the range of this function. Which means that these are the elements, whichever one you pick from here, that element has not been, is not the image of any of the elements in the domain of the function. So you could say that, for example, you could pick any element over here, for example, negative 2. So you can say that consider, for example, an element negative 2 in codomain R. In codomain R, right? Now it is you know that basically you know that f of x is equal to 1 plus x squared. F of x is equal to 1 plus x squared is positive for all possible values of x. Right? So f of x is equal to x squared is basically 1 plus x squared. Whatever sort of x you pick here, whether your x is negative or positive, x becomes a positive number because you're raising it to the second power, and then you're adding 1 to that, so you're going to end up with a positive number, right? And so negative 2, so then you can say that there does not exist any x in domain R, such that f of x is equal to 1 plus x squared is equal to negative 2. And therefore you can say that f of x is equal you can say that f is not surjective. And of course, since basically f over here, we argued that f is was not 1 1, and it's also not surjective, so then you can say that f is not bijective. Now if you want to show the same thing, basically the argument that this is mainly a counter example that we have created here based on the graph of the function and based on some single number, basically. Now if you want to do this using algebra, in the beginning of the problem I told you that you could get into trouble because you're dealing with the second power of x. Such expressions get a little bit, they're not complicated, but they could get you into trouble because you could make sense of the algebra in a wrong way, and that basically that would be a mistake, of course. Meaning that suppose that you have your function is f of x is equal to 1 plus x squared, and you want to know whether this function is surjective or not. Now using the method that we had before, if I say that f of x is equal to y, and if I write y is equal to 1 plus x squared, and if I try to find x in terms of y, I would get x squared is equal to y minus 1, which and if I took the square root of both sides of this equation, if the square root of x squared is equal to the square root of y minus 1, that would give me basically so you know that your x could be a negative value, a positive value, and therefore the output of this function could be plus or minus x. That's plus or minus x. And it doesn't really matter whether y is a negative value or positive value. Let's suppose for the moment that y could be a positive value as well, meaning that I simply write this as basically y minus 1, which is of course not the case here, but just for the sake of argument I write it that way. At the end of the day, you can simplify this expression to plus or minus x is equal to y minus 1, right? So that means that basically that means that here in this function we have f of x is equal to basically f of x is equal to oh, I did make a mistake here actually. Let me so I cannot, of course, take the square root of y minus 1 this way, right? This is actually not possible. So I have to write this as the square root of y minus 1, right? And since that is the case, I can say that basically x is equal to plus or minus the square root of y minus 1. Now what that means is that since your f of x was basically 1 plus x squared, you could say that f of basically the square root of y minus 1 is going to give you y here, and also f of negative the square root of y minus 1 is again going to give you y here. And as you can see, it's a little bit hard to make sense of this situation. At least I tried, and I did get into trouble. So in such cases where you can see that you're not actually sure whether what you're saying is actually right or not, you can simply, if there is the possibility not to do it, you can just simply not do it and then go back to your function as we did here. Take a look at your function. If you can see that your function is basically, for example, you can see that based on your function, for example, there are all of these values that are not basically a part of the range of your function. And so what that means is that then you can basically you can create some argument here. For example, negative 2 is not a part of your function, and so that's basically negative 2 cannot be the output of the function, and so then that way you can solve the problem. So that's basically, that was question number 7. And so in the next video we will talk about the rest of the problems. I'll see you in the next video. Thank you.